Thanks so much. I guess thanks so much for the introductions. And today, basically, I'm here to share a little bit of thought on, like what kind of things we learned over the last few years in designing and applying these kind of deep learning frameworks. So I think it all started with kind of like in 2012 when we thought that all those kind of image classification, understanding, and those kind of problems become really hard because like we know that we can geotag stuff, but we cannot understand what kind of things are conceptually easy for us to do. And luckily, in the last few years, what happened is that we have a series of papers and research that made it really easy. And today, like we kind of go to, like, say, Google Photos, and we search for all our photos of kids and cats and dogs, cats, of course, and very easily, and we take it for granted, right? And now, with all these kind of process, one big problem that popped up was basically that researchers need to catch up with all these kind of awesome research so that we can iterate on those kind of results. And at the same time, companies want to basically go in and say, like, I want to take that paper, that awesome paper, and then apply it into my products, whether it be image understanding, ads, or self-driving cars, which is going to be shaping our transportation in the next decade or so. And I think, like thinking back a little bit in the old days of when I was back at Berkeley as a postgrad student, we kind of started this Caffe project as a kind of like a pretty small academic project that started to, in order for ourselves to do all kinds of research. And to our surprise, in some sense, it started by doing computer vision really well, but it got very quickly adopted by a bunch of industry participants, and in some way it became a very popular deep learning framework run by a nonprofit, and that's of course because of a huge community that we're having to kind of like contributing and using and evangelizing Caffe, and we're really grateful about that. Everything you want to know about Caffe is probably going to be like found on the cafe.berkeleyvision.org webpage, and we have a cute demo on demo.cafe.berkeleyvision.org, and that cute cat is always kind of like staring at you if you want to go and check out some demos. But we're probably not here to talk about, like the Caffe, and you've probably heard about it in multiple occasions, and you probably already used it in your actual work. So I think, like one thing that's kind of pretty interesting for us to ask is, if we're going to be thinking about the future and think about a question, what kind of things will make a much better deep learning library if we are going to be looking, 5 years, 10 years next, right? Because a few years ago it was basically just a research tool, but today it is actually changing a lot of the industry and making very deep impacts in all parts of our life. So I was basically kind of like thinking about what we should summarize. My goal about a better deep learning system, I coined this term called max. And I'm going to be talking about each individual character actually in the reverse order, but I kind of thought that I shouldn't be using the name spam. So here's max. First of all, scalability. A few years ago, we had one GPU sitting on our desk and we're happy as a clam. Today, pretty much, a lot of questions pop up on the Caffe users group, and one most important question is, how do I train multiple GPUs? Well, train on multiple GPUs, because I'm such an effing big data set, and it's just like not enough for us to use one GPU or even 8 GPUs on one machine, right? And mathematically, actually, things are pretty easy in some way, and nowadays a lot of frameworks already employ different methods for us to do scalability, to speed the train, and things like that. And if we think a little bit, the abstract math, what happens in neural net is that we have a network and we run the forward paths, we run the backward paths, and we get a gradient, which are the directions that the parameters need to go to make it better. And we update these kind of parameters, one set of parameters per layer. Now, with multiple machines, basically what happens is that we have the notion of a virtual large batch, and then these kind of things get carried out on each machine, and like this big batch gets distributed onto different machines. And what happens is that each machine basically kind of like knows a little part of the gradient, and they need to do a function called kind of reduction, which is basically saying all those machines start to talk to each other about their gradients, and they accumulate all those gradients before they do a batch update. Now, of course, if we're designing a modern framework such as like some improvement of Caffe or Torch or TensorFlow or MSNet, a rational choice is for us to pipeline stuff so that we don't need to kind of wait for everything to finish before we start updating and communicating and things like that. we use the typical technology where we wait for something to be ready and immediately start communicating and things like that. Now, it turns out that these kind of things is not really new. In the old days, when we think about atomic bombs, financial labs, and things like that, there is a software principle, or a software package called Message Passing Interface, or MPI. And the thing that we're doing is exactly basically what they call origins, taking a chunk of memory on each machine, have them talk to each other, and then basically get the mixed version of it. Now, the high-performance computing community has done a really good job in optimizing this computation. There are three basic approaches which scales logarithmically with machines. There are even better methods such as ring-based methods, and as long as you have a large enough chunk of memory, actually the speed is irrelevant of the machines that you use. And by employing these kind of approaches, literally every framework that we see today obviously having a very nice scaling factor. Which comes to my point. There are a great number of really nice libraries that does all those kind of optimized communication and stuff out there. There is OpenMPI and NBA PICH, which you might be very familiar with if you're in PHP land. There are new libraries such as Nickel, which basically, very great library from NVIDIA, which makes very efficient GPU-to-GPU communications. And of course, you can even basically write this kind of software protocol yourself using libraries such as CMQ and things like that. Basically, there are recipes out there, and we framework writers are basically, we should basically piggyback on these kind of great results. Now, moving on to P, which I call it portability, and Rajat actually already made a very great point that today, when we think about the computer industry, we're not really thinking only about, the very mysterious clusters living in, Oregon or Atlanta or something else. We're actually thinking a great amount of things, the cloud being one, the laptop being one, and I see a lot of us have cell phones, and we take it for granted that, they are actually super powerful computers today. And in some way, AI it's very abstract. It doesn't really care about what kind of things it runs on, it's basically pure math, right? And very plausibly, today we want to put these kind of AI algorithms from the cloud to, phones, to our watches, to our IoT devices, to detect cucumbers, to do all kinds of crazy stuff. And that basically means that we want a framework that will be, we want frameworks to be more portable. And no one really wants to drag a laptop, drag a huge GPU machine everywhere. And ideally, what we want is, we basically want to have a model, and then basically say, if we're running on the cloud, we call the cloud side. If we are running on Android, then it's probably Java, so we write some Java code, but essentially the math is going to be the same. And we just want to, basically design the model once and deploy it everywhere. There are multiple ways of doing it, of course, but proper abstraction that we have seen in the recent developments of the frameworks are, I think, doing a pretty good job. And now, often we can see things like, I would love to share this, which is one slide about. So there are still a lot of challenges, of course, in designing portable systems, right? Let's think about phones. There is a very limited computation. The battery life is a very important thing because we don't really want to, get out of the battery, and especially if you're based in a foreign country and your phone dies, it probably means the end of the world to us. And of course, right now what we are doing is our models are really luxurious. If you think about the things that we do for, say, Internet Challenge, we always kind of design really large models so that we can squeeze out the last bit of accuracy out of these models. But in some way, if we think in a portable mind, actually a lot of things can be cut off, and we can actually use very small models to achieve the same goal that we can do, or similar goals that we can do with a very large model. And of course, there's a lot of, ecosystems, tooling, and things like that we need to build, which is probably the task of the community in the next year or so. And I would love to share this thing, which is basically, at Facebook, we kind of thought there's all kinds of very crazy ideas about artistically rendering the videos and things using, famous paintings such as Van Gogh, things like that. There are very great papers pioneering coming out since 2014, but a lot of them still actually run, on a pretty expensive server. So we thought, it's possible for us to put it on the phone, and we started about mid last year. And right now we're actually, shipping these contents on our main Facebook app. what happens is that you can basically run these kind of artistic rendering 720p real time on a phone, and that kind of creates a very nice augmented reality experience for people. And this is only one application of even mobile, because once you have this, we can think about all kinds of other things that could happen. Imagine any kind of AI algorithms you can run on the server, tomorrow potentially run on the client, and that opens a lot of possibilities. Again, under all these applications, essentially, the frameworks are basically doing a lot of computations. And what we are seeing is that, we used to be thinking in the fashion of very luxurious float numbers and things like that, which was fine for, research, but, when we are going into an industry use case, we find that there are way more things that we can do to design a more efficient and more, powerful system. And in the recent years, what we see is that there's a lot of research themes that are popping up around quantized computation, sparse math libraries, using model compression to get a really small model from big models. And also we're kind of rethinking the existing operations that we are carrying out in deep learning. And let's take quantized computation, for example. Float numbers, in some way, we take it for granted that this is the default, data type that we use for deep learning. But it's very big in some way. It's extremely accurate, and in some way more accurate than what we need. AI algorithms are kind of known to be kind of sloppy because all those parameters are initialized at random, and then we figure out what exactly they will be based on a massive amount of data. And what happens is that it doesn't really matter sometimes for us to be a little bit off on the computed values. And what happens is that if we use lower bits, then most likely things are going to be at the same accuracy. The benefit of that is that if you think about, running things on phones and things like that, float numbers take a lot of picojoules to compute. In comparison, if you want to add two float numbers, it takes about 0.9 picojoules, and if you take just two fixed U8 numbers, it takes only 0.03 picojoules to do one addition. And those kind of things become really, really crucial when we want to reduce the power, when we want to put things into more exotic hardware and things like that. Of course, this comes with a lot of challenges because a lot of our optimized libraries today are written with float numbers and things like that. So that kind of adds a lot of challenge for us to write optimized libraries for those kind of things. It's also very efficient, with new kind of hardware. NVIDIA shared this very nice very nice graph showing that if we can reduce precision and if we can combine it with new hardware, then it's possible that we can achieve a much better throughput per second per watt performance, and that kind of matters a lot in other applications. The other thing is that research has never been stopping in the AI field, and one thing that I find really amazing is that we are always rethinking what kind of computations we can do. And if you have been playing with AlexNet in the last few years, you probably remember there's a very exotic term called group convolution. Now, very initially, Alex designed this group convolution because he has two GPUs, and it's not possible for him to put the whole model onto the same GPU. So group convolution was actually designed as a way for us to, to cope with memory constraints. And recently, Tiny Will from our Fab research lab found that actually there's some alternative interpretations of group convolution. And what he did in his most recent ResNext paper is that he took this group convolution idea into an extreme and say, instead of doing two groups, I'll do 32 groups, and each group is extremely tiny convolutions, and that achieves a much lower number of flops needed for the computation and still a much better performance. So I think these kind of new research ideas are continuing to become iterated with our engineering designs and with even further research to push this field forward. A lot of challenges, as we talked about, today we have a lot of libraries that are already creating these kind of reduced precision computations. IBM did a pretty nice one. We used it in TensorFlow and it was not great. There is cuDNN with new reduced precision computations. At Facebook, one of our interns designed a system called NMPAD, which delivers a very high performance computation on mobile devices, and there's GemsOP also coming from Google and Creator of IBM that does intake computations on the server side as well. There's a lot of challenges, especially research-wise. How do we convert all those kind of research results today basically assuming flow numbers and things like that, into these kind of reduced precision computations and things like that. How do we efficiently train those kind of models? How do we tune performance with new algorithms and new hardware that we should do with these kind of things? But at the end of the day, one thing that I want to point out is that things are becoming way and way more modular. The thing that we found in the previous points, like the scalability, the portability, and the augmented math, is that a lot of components in deep learning are actually being able to be reusable across different frameworks. Coding learning is probably one of the most prominent idea of this. Back in 2013, I think when Caffe came out, we were kind of a little bit fortunate in that we were the fastest GPU runtime back then. And then NVIDIA came in and was like, let's change it. And NVIDIA wrote cuDNN, which is extremely nice, extremely fast, and it quickly became the kind of standard CNN backend for all kinds of frameworks on the GPU side. And it really helped all these kind of frameworks to be running at about the same speed. And looking back in time, in 2013, what we were seeing is that frameworks are basically doing their own work. Caffe has its own optimized math libraries, Torch has it as well, CM has it as well, Today, what we're seeing is that we probably are embracing Unix philosophy more than ever before. What happens is that we're getting frameworks, and hopefully we're going to be continuing to be getting frameworks and kind of abstracting out into different components, ranging from databases that deal with all kinds of data, to the core math library that does the actual computations, to communication libraries such as Nickel, ZeroMQ, Redis Qs, and things like that, to low-level computation frameworks such as like CUDA, OpenGL, OpenCL, and things like that. And we're also embarking on the idea of compilers under shares the XI idea. I think there is another project that's pretty nice called NVM from the Amazon creators. And on top of that, we're basically putting the framework that connects everything and abstracts out everything so that as an application user, we care about the math, we care about the logic, and we stay assured that these kind of different components developed by different experts are going to be ensuring us a holistic solution, right? Think about, let's pause for a moment and think about how we built Boeing, planes. There's no one single company that built Boeing. There's a lot of companies doing great components, and then when combined, create Boeing, this awesome plane that we fly around every day and without any accidents. So I think, as we are stepping into the world of deep learning impacting a very large amount of parts of our lives, then we're probably going to be, creating awesome engineering practices that's pretty similar to what we did with Boeing and all those kind of conventional approaches. The take-home message is, I would love to share this idea about the MAP framework, and I think we've been seeing a lot of trends happening, and with these kind of modularized designs and focusing on all kinds of different components that are crucial to deep learning, I think we will be having much better and better framework designs. One thing that people often ask me, and that's I promised the last point, is that people often ask me, what should I choose? In the back in 2013, people asked me, should I choose Caffe or Torch? Today, people ask me, should I choose Caffe or TensorFlow or MSNet or a lot of others, chain and things like that. I think, my feeling, and I've always been kind of contemplating about this, what is the silver bullet for us to solve all these problems? And I kind of feel that, in some way, because deep learning is such a big use case right now, there's a range of different applications that we need to kind of serve for different purposes. For industry use cases, it's very super stable and things like that. On the other side, on the research side, things are super flexible. So maybe there's really no single library that could meet all those kind of purposes. At Facebook, what we tried is basically we use mainly Caffe and Torch to cover a wide range of these applications. I think soon it's going to be talking quite a bit about the awesome things that we did on the Torch side. But in general, I'm really glad that we're keeping a very open and collaborative environment for deep learning. And I would like to end with this quote from the Solvers. In open source, we feel strongly that to really do something well, you have to get a lot of people involved. And everyone in this room, we have done a really great job. We get ourselves involved and we contributed to this big effort. And to this, I would like to end my talk, and I'm really deeply grateful to everyone attending today. Thanks.